All right, so thanks to everybody for joining in this afternoon. I'm going to go ahead and share my screen. Sorry, I shared, but I had my mute on mic. So let me go back and share again. Um, could somebody just unmute and let me know if you're seeing the home page?
I can see it.
Thank you very much. All right, so let me go into the weekly overviews. Oh, I did it again. Let me do this as soon as I get a moment. Bear with me. I'm having to do a little backdooring because I logged into RTCC again. So let me just do this to get us started. And then once I get a moment, I'll go ahead and log in a different way. But keep us moving forward. Let me just do this. All right. So here we are, the weekly overviews. And you can see this week we have two overviews to cover: Newton's laws and gravitation, and the project article deadline. So we'll deal with gravitation and the project article approval on Wednesday. Today, my goal is to get you through the Newton's laws overview. And then, as I said, Wednesday, we'll pick up the other two. And I'll talk to you about the midterm. I'll just kind of briefly talk about it so that when it opens Sunday, you will, Saturday, excuse me, when it opens on Saturday, you will, be expecting it and know how to proceed. So, all right. So, before I do that, just as a reminder, if you recall last week, because things ran a little bit long, I adjusted the due date um, on the 2D motion discussion. I gave you until tomorrow at 11:59. That way, you would have some time to digest that material and reach out to me if you had questions. So don't forget that the discussion on 2D motion is due by tomorrow, and then we'll be following our regular schedule for the remaining discussions and problem sets that are due on Saturday. So I just wanted to, bring that to your attention so that everybody would be mindful of that deadline. All right. So now I think we're good to move forward. So again, at any point, if you have questions, don't hesitate to stop me. Since I'm working on a different computer, I don't have the capability of having the Zoom window on my screen while I'm sharing. So I can't see anything that's happening on screen except that I'm sharing. So don't hesitate, unmute, ask me any questions you have at any point during the presentation. That's not a problem. All right. So this week we're going to be starting to integrate forces into our description of moving objects. Up till now, we have been dealing with moving objects from a kinematics perspective. And you remember, kinematics means pure motion, right? We don't worry about the cause when we deal with a kinematic description. And so we've been dealing with things like position, distance, speed, velocity, acceleration, displacement, but we have not focused on the causes for the motion. And so now we're going to be utilizing forces, and we're going to look at the rules that and laws that govern forces so that we can include in our description of moving object the causes for the motion. And so you can see here the laws that help us to deal with the causes for motion are Newton's laws. And so we'll be learning about forces, and we'll be learning how to utilize Newton's laws to explain motion or analyze motion or give a quantitative description of a moving object. And also we'll be looking at, the kinds of calculations that we can do utilizing Newton's laws. Okay, so don't forget, these are activities that you have on your plate that are due by Saturday. You can see here you have problem set 5. Now, just to remind you, problem set 5 actually deals with 2D motion. It's problem set 6 and 7 that are going to deal with Newton's laws. You do have a discussion on Newton's laws that's due by Saturday, and your first bonus is also due by Saturday. So let me talk about Newton's laws for a bit, and then we'll come back and take a look at that first bonus. Okay, so that's what's on our plate to get through today. If you click on the required readings viewings tab, you see that chapter 5 in your textbook deals with forces and Newton's laws. So you'll want to read that. I have a series of videos that deal with Newton's laws, and you'll want to watch them. I have a NASA website that deals with Newton's second law as well. Again, those first 3 items are all reference materials and reading materials that you can utilize. What I'm going to focus on are the supplemental notes. That's what I refer to as my lecture notes. Somebody unmute and tell me if you can still see the screen.
Yes.
Thank you. Okay, because I'm putting it in full screen because I'm on my laptop, and that's a little bit tricky to navigate sometimes from within Canvas. So I just wanted to make sure you're seeing that. Now, I'm going to highlight this screen just for a moment, the How to Study module. If there was ever a time when you needed to be diligent about approaching this material and how to study this material and utilizing these items I have listed here to help you, this would be a time for it. Newton's laws is the heart of what this course is about, because we are dealing with Newtonian mechanics, as I mentioned to you several times already in this course. And so without a fundamental understanding of Newton's laws, it's really difficult to properly analyze motion beyond the simplistic descriptions that we've already done. Okay. So if you aren't being diligent and putting in the time and the effort into, getting comfortable with this material and, doing the discussions and the problem sets and asking questions, and reviewing the reading materials and the video materials that I've made available, I would suggest to you that this is a really good time to do that because, well, I'm not going to say that what we've been doing up to now is easy because I recognize that it's new and challenging for students who've not seen it before. But the material is not going to get any easier from this point forward. And if you don't have a strong foundation where Newton's laws are concerned, the rest of this is going to seem like gobbledygook. I'm just being honest with you. Okay. So please take heed to how to study and use it to your benefit. Okay. So you can see by the title here that we've moved from studying things from a kinematics perspective to studying things from a dynamics perspective. Okay. And dynamics is a way of saying we're looking at the causes for motion. All right. And as I mentioned, that involves understanding force and it involves understanding Newton's laws because they help us to understand how forces interact and affect motion. Okay. And so that's what this is talking about. Kinematics is a description based on their displacement, velocity, acceleration, but we don't talk about what's responsible for the motion. Dynamics, on the other hand, provides us a way of understanding the causes and control that forces play where moving objects are concerned. And so we'll need to understand key ideas like force, mass, and inertia. Now, we've looked at the idea of mass before, but we've only looked at mass from the perspective of it's a fundamental property, and we want to deal with it from a units perspective. But now we need to understand exactly what is mass and what role does it play in this, in terms of analyzing the motion of an object. And also this word inertia, we've got to get a handle on that as well. And so you see they give a little bit of a historical perspective, right? Galileo was one of the important individuals in terms of helping us understand motion. He was one that experimented to try to determine the causes for motion. And he got a good number of things right, but there were some things that he had fundamentally incorrect. And so along came Newton, literally 100 years, the year Galileo died, Newton comes along and, and during his lifetime, in the latter part of the 1600s, he was instrumental in helping us to understand motion. In fact, much of what Newton uncovered through his investigation, and I should say theoretical investigation, is utilized today to help us, analyze motion. In fact, things like putting a man on the moon or Mars, a rover on Mars, the advancements in our understanding of automobiles, a lot of those things aren't possible without the work of Isaac Newton. And so that's why we call it Newtonian mechanics. And so you can see here, we do consider him perhaps one of the greatest minds to ever live. In fact, if you want to know how genius he is, in order to describe moving objects, he helped to invent calculus to do so. So he invented a whole branch of mathematics to help him understand physics. So the force, as I said, is premier and central in explaining motion from a dynamics perspective. And yet, it's not this foreign concept if you really think about it. I mean, you get the idea of what we mean regarding force, maybe not from a technical mathematical analysis perspective, but a force is simply a push or pull. And I'm sure in your lifetime you have pushed or pulled something, right? And so you have some experience in this area. And so what we're going to do is build on your everyday experience so that you can then um, give a more quantitative usage regarding forces. Okay. And so since force involves a push or a pull, intuitively we know that that has to have a direction. If you push or pull something, you have to be pushing or pulling in a certain direction. And because of that, force is a vector, right? So force utilizes all those great rules that you learned about vectors last week when you delved into the vectors overview on your lonesome, right? Because that you were tasked to cover the vectors overview on your own based on some information that I shared last week regarding vectors. And so we know that every vector has a magnitude and a direction. So since force is a vector, every force has a magnitude and direction. And so sometimes you see the bold capital letter used to indicate that a force is a vector. That's a useful way of distinguishing it from, scalars, right? Because we know that scalars do not involve a direction, and we need a way to be specific. And so we can use arrows to represent our forces because we can use arrows to represent vectors, and we use bold when we're looking at it in print to distinguish that it's a vector property. Although I don't expect you to have to utilize bold when you're writing or anything like that. So don't worry about that too much. But you do have to worry about the fact that anytime you're going to express a force, you have to be mindful that you have to have a magnitude, which is the size of the force, and you have to have a direction. So, so because we can represent forces as vectors, we can add or subtract them just like we do any other vector. Okay. So when you add up multiple forces, what you get is a resultant force. So you can add and subtract forces. If the forces are pointing in the same direction, you add them together. If they're pointing in opposite directions, then you subtract them. And when you add or subtract vectors, add or subtract forces, you get a resultant force or the net force. That's a very important term, the net force. Okay, the net force is what you get when you combine multiple forces. That's an important concept because we'll see here shortly. It is the net force that actually affects or changes the motion of an object. We'll see that here shortly. Okay. Now, we need to be very clear that when we're dealing with moving objects and we're dealing with forces, we focus on the external forces. And those forces act from outside of the object. And they are the ones that can impact the motion. We do not focus on internal forces. because if our goal is to analyze the motion of the object, internal forces play no role in that. Okay, so we focus on the net external force, the net external force, because that is what can impact the motion. Another tool that we use when we're analyzing forces, in addition to our knowledge of vectors, is to draw free body diagrams. And so a free body diagram is a tool that helps us to visualize the forces acting on an object. Okay, so you can see in the picture here on the right a free body diagram, and you can see this small little dot. It looks red. You can see the red dot on the picture, and you see these two force vectors because we're representing them using arrows. And you can see that there's force number 1 and force number 2. And we can see that they point in different directions because the arrows point in different directions. Okay? Now, you might be asking the question, what kind of object is being represented by the dot? The answer is any kind of object. Any kind of object that we want to analyze the motion of, where forces are important. So we can imagine that dot being any object. What we imagine doing is taking the object and collapsing it into a dot. So that little red dot could be representing the Earth. It could be representing a car. It could be representing a person. It could be representing an object sitting on a table. It could be representing any object. We imagine taking that object and collapsing it into a dot and then showing the forces acting on it using arrows to represent our force vectors. So you will have to draw free body diagrams, though there will be simple ones, to help you visualize the forces acting on an object. All right, so now let's take a look at Newton's laws of motion. So Newton has 3 laws that explain and predict the dynamics of motion. In other words, 3 laws that help us to explain how forces, interact with objects to affect their motion. And, he came up with these 3 laws based on observation and insight. That's just another way of saying he did it from a theoretical perspective. In other words, Newton wasn't much of an experimenter, if you will. He was what we call a theoretical physicist, okay? And as I mentioned, he built on the work of others. Galileo was one and Kepler was another. And we'll see how he built on Galileo today. And then on Wednesday, when we talk about gravitation, we'll talk a bit more about how he built on the work of Kepler. Okay. And so, he was humble enough, even in his genius, to give credit to Galileo and Kepler. And you can see his statement here: if I have seen further than other men, it is because I have stood on the shoulders of giants. Now, think about in your lifetime how many times you might have heard somebody said, we're standing on the shoulders of giants. That came from Newton in his acknowledgement of the work of Galileo and Kepler. Okay, and you see on the bottom here, it talks about, in the last paragraph, it talks about the fact that, he also discovered the law of gravity. And so his 3 laws of motion, along with the universal law of gravitation that we'll see on Wednesday, is like, this package that really allows us to fully explain motion from a dynamics perspective. So his first law of motion, Newton's first law of motion. So I'm going to state it as you see here, and then I'm going to read it to you in a little bit different way to try to break it down a little bit for you. Okay? So it says Newton's first law of motion can be stated as follows. A body at rest remains at rest, or if it is in motion, it remains in motion at a constant velocity unless acted on by a net external force. Okay? So let me read it a different way for you, and then we'll get a little bit deeper. A body at rest remains at rest unless acted upon by a net external force. So if the object is at rest, it is going to remain at rest unless you act on that object with a net external force. So if it's not moving, it is not going to move unless you disturb it by applying a net external force. It doesn't say a force, it says a net external force. Okay? So you can apply forces to an object, but unless those forces combine so that you have a net force, you cannot alter that object that is at rest. Okay, that's one half of the picture. An object in motion remains in motion at a constant velocity unless acted upon by a net external force. So if it is moving, it is going to keep moving with the same velocity unless you disturb it with a net external force. Another way of saying that is you can't change the speed or the direction of an object unless it is impacted by a net external force. Again, Newton is not saying that forces will change the motion of an object. Newton is saying what? A net force will change the motion of an object. So he gives two possibilities here in his first law. The object can be at rest or it can be moving with a constant velocity. Remember, constant velocity means what? Don't hit the gas, don't hit the brakes, don't change the direction. So if it's moving with a constant velocity, that is also a possibility here. And either of those scenarios will not change unless you provide the object with a net external force. I always tell folks, Newton is famous because he came up with a formalized way of saying books don't jump off tables. Think about it. In your house, there are probably lots of things at rest sitting on tables and other places. And Newton's first law says those objects are not going to move unless you provide them with a net external force. There are forces acting on those objects that are stationary. They are balanced. You could have an object moving it with a constant velocity. There are forces acting on that object that is moving with a constant velocity. But those forces also are balanced. So he is saying, if you want to change an object's motion, you need an unbalanced force acting on it. Okay? And so Newton's first law states that there must be a cause in the form of a net external force in order to change the velocity of an object. And this can be changed in the object's speed or its direction or both. Now, a lot of people intuitively recognize that an object that is at rest is not changing its velocity. But just think, an object that's moving with a constant velocity is also not changing its velocity. So if you want to change an object's velocity, what do you need? A net external force. Okay? So now, be mindful of that, because remember I told you Galileo had a lot of things correct, but the one thing he got wrong was his idea of friction. You see, because he thought that the natural tendency of an object is to come to a stop. And so if that's the object's natural tendency, you don't need to worry about friction. But he got that wrong, because what Newton is in fact saying is an object's natural tendency is to keep doing whatever it's doing. And if that happens to be at rest or moving with a constant velocity, there still could be friction involved. Okay? And so because Galileo failed to properly account for friction, we had to wait until Newton came along to properly explain that to us. Okay? Sometimes you'll hear Newton's first law referred to as the law of inertia. And that is the tendency of an object to remain at rest, right? Or in motion with a constant velocity. So inertia is the tendency of an object to keep doing whatever it's doing. Okay. Now, how do we know that, the amount of inertia? We look at the mass of the object. Okay. Because we know that some objects have more inertia than others, because some objects are more difficult to change than other objects. And they give the example of a large boulder being more difficult to change than that of a tennis ball. And so that's because the large boulder has more inertia or more mass. And so here now we have our first formal definition of mass, and that is the measure of the quantity of matter within an object. And we measure that, we know, in kilograms, because mass is one of our fundamental properties, right? But mass tells us how much inertia an object has. And objects with more inertia can put up a bigger fight, if you will, to continue doing whatever they're doing and not have their motion altered or changed. Okay. And so we'll see on Wednesday that these objects that have more mass and more inertia also have a greater gravitational force when they interact with other objects. Newton's second law of motion. And so what the second law does is allow us to mathematically analyze that cause and effect relationship between force and changes in motion. In fact, we need to, fix in our mind this idea of what do we mean when we say changes in motion. Well, we can package that whole idea of changes in motion into one word, and that's acceleration. So what we're looking at in Newton's second law is the cause and effect relationship between force and acceleration. You see, Newton's first law establishes the conditions that need to be present in order for an object to change its motion or accelerate. Newton's second law allows us to mathematically calculate the amount of acceleration. And so, so you can see the relationship between net force, mass, and acceleration in Newton's second law. And that is the equation F net equals ma. If you recall way back to our understanding of the nature of science, we said what? That what a law does is focus our attention on a particular pattern in nature. And the pattern that we are exploring here in Newton's second law is the pattern that shows how forces and acceleration and mass are related. So we can see from the formula F net equals MA. Sometimes you just see it in textbooks written F equals MA. Same thing, because it's understood that the only way you can get an acceleration in the first place is through having a net force. Okay, so F net equals mass times acceleration. So we can see from this relationship that if the net force gets bigger, the acceleration gets bigger. We can also see from this relationship that if the mass gets bigger, the acceleration gets smaller. And that's what they're showing you in the illustration in the picture. You can see that they're pushing on the basket, the person in the picture is pushing on the basketball and the SUV with the same amount of force. How do I know that? Because the length of the force arrow, the length of the force vector is the same. So if the length of the arrows is the same, then the amount of force is the same. But you can see, because the basketball has a much smaller mass, the acceleration vector A is much bigger. You can see by looking at the SUV, because the mass is much bigger, the force isn't going to produce as much acceleration. And so the acceleration vector A, or the vector arrow, is much smaller, right? So that's what Newton's second law allows us to do. So the first law creates the conditions that need to be satisfied in order to accelerate. The second law helps us to measure the amount of acceleration, or I should say calculate or quantify the amount of acceleration. All right. So now in these last remaining slides, what I'm going to do here is I want to, we want to take a look at some specific types of forces. Okay. And so the first force we're going to explore on a simplistic level is that of gravitational force or weight. Okay. Now we know already that gravity on planet Earth produces an acceleration minus g, because we know that, gravity pulls an object down and produces an acceleration negative 9.8 meters per second squared, right? Free fall. Okay. But now if we take that same acceleration minus g and we utilize that with the object's mass, we use that in concert with the object's inertia, we can calculate the object's weight. So weight is the amount of gravitational force on an object's mass. Okay. And so to calculate the weight, W, which is a vector, we multiply the object's mass times minus g. Okay. Now we do need to understand a few things about the difference between weight and mass, because a lot of times in everyday conversation we use them interchangeably, and that is possible because there's a fixed relationship between weight and mass. Okay, and that is because on planet Earth the gravitational acceleration is fairly constant at 9.8. But we need to understand the difference, because now we're moving beyond how we use things in everyday conversation, and we're utilizing, we're being more specific. Okay, so we need to understand that mass is a scalar. It does not depend on location. It does not have a direction. Mass is an intrinsic property, and therefore your mass will be the same no matter where you go in the universe. Your mass is the same on Earth as it is on the moon, as it is on Mars, as it is anywhere in the universe, because it is not location dependent. Your weight, however, depends on gravity, and gravity changes as you move around. Okay, so your weight will be different on the moon than it is on planet Earth. In fact, on the moon, you'll have a weight that is 1/6 of what it is here on Earth. Same thing on Mars, your weight will be less. On Mars, the gravitational acceleration is roughly about 3.75 meters per second squared. So a little bit less than, 3 times, right? 1/3, excuse me, a little bit less than 1/3 of what it is here on Earth. Okay. So, again, mass is not location dependent. Weight is location dependent, and it depends on the gravitational field. Okay. And so we already know that when we just focus on the acceleration of gravity alone, no air resistance, the object is in free fall. But now we know how to take that acceleration and combine it with the object, or multiply it times the object's mass to get its weight. And so now we have a new unit. So you should be pulling out those index cards and writing this new property, force. And you should also be writing down the metric unit, which is the Newton. And you'll see here they abbreviate it with a small n, but most books, out of reverence for Isaac Newton, capitalize his name, and they use a capital N to represent newtons. Okay, but either or, the idea is that the unit is the Newton when we're dealing with force in the metric system. In the English or British system, you're familiar with pounds, and that is the unit for weight in the British system. And so, in fact, when you think about, when you're going to the store and buying a 10-pound bag of potatoes, that is actually the weight of the potatoes and not the mass. So we have to be, mindful of that. Okay. Newton's third law. So Newton's third law deals with the idea that forces exist in pairs, and it looks at the symmetry of forces. And so we can state Newton's third law of motion by saying, whenever one body exerts a force on a second body, each body experiences a force that is equal in magnitude, but opposite in direction. Equal in magnitude, but opposite in direction. So in one way of thinking about it is, anytime one object pushes or pulls on another object, that object pushes or pulls back with the same amount, same magnitude, but those forces point in opposite directions. And so you can see in the picture that the swimmer is exerting a force on the wall with her foot. And we can see in the picture that in response, the wall exerts a force back on the swimmer's foot. Now, those two forces are the same size. And you can see that because the arrows are the same size. You can see that they point in opposite directions. What you don't readily see that is important here is that those action-reaction force pairs do not cancel each other out. You might be tempted to think that the forces in that picture are balanced. They are not. We know that the swimmer is going to accelerate. Otherwise, the swimmer would just stay in place. We know that doesn't happen. So the swimmer uses that push on the wall to create, thrust forward, right? And that happens because those two forces, although they're equal in size and opposite in direction, are not canceling each other. And that's because they are not being exerted on the same object. The swimmer is exerting a force on the wall. The wall is exerting a force back on the swimmer. In order for those forces to cancel, they would have to both be acting on the same object, either both acting on the wall or both acting on the swimmer. That is not the case. So the other thing that's important that goes along with Newton's third law, this idea of action-reaction pairs, is that those action-reaction pairs cannot cancel each other out because they do not act on the same object. Some other important types of forces that you'll come across while you are utilizing Newton's laws. And so push, pull, which we've kind of talked about. Thrust, I just mentioned in from the picture of the swimmer. Lift, drag, those are forces that the lift, when you're thinking about birds in flight, for example, or an airplane. Drag, a lot of times you'll hear drag referred to as a air friction. Weight, we just looked at. Friction. Friction is a very important force, and we'll look at it in just a moment in a little bit more detail. The normal force is an important force as well, anytime objects are in contact. And tension. Tension is typically the force we associate with cables and wires and strings and so on and so forth. Okay. So friction. So friction is any force that arises in opposition to the motion of an object, whether that is the object wants to move or the object is moving. So this opposition force, this friction force that opposes motion between stationary objects is called static friction. The friction force that opposes motion between moving objects is called kinetic friction. And so a lot of times, people don't realize that for an object that is stationary, there is actually a friction force that plays a role in maintaining that at-rest status, and that is the static friction. Okay. And so, again, as I mentioned, this is the force that Galileo could not account for, did not properly account for. And so, it is like anytime things are touching, there's friction. Even though you don't see it, you don't readily see the push or pull, is there between surfaces. And so you'll see that it's given kind of this special symbol, and that's the lowercase f. We utilize that to denote friction. So remember, friction happens between surfaces that are in contact, and it opposes the motion. So for an example, if an object is moving to the right, friction is being exerted to the left. Okay. We also have spring forces and restoring forces, but we'll talk about those much later when we talk about Hooke's law and we talk about harmonic motion and penduli and so on and so forth. So, we'll get to see that later on, so I won't focus too much on it now. Normal force. This is another one of those special forces that is present when objects are touching. So anytime an object is resting on a surface, gravity pulls on that object and exerts a force on that object, creating the object's weight. So you can see the picture on the right where the dog food, the Bow Wow child, is sitting on a table. Gravity is pulling on it, exerting a weight down. But there's also a response force on the Bow Wow child, and that is the table pushing up on the dog food, right? And we call that the normal force. And we use the symbol N to represent, capital N to represent the normal force. Okay. So, and this arises because of Newton's third law. The Bow Wow child pushes down on the table pushes back. Okay. So the Bow Wow child on the table is the action force. The table on the Bow Wow child is the reaction force. The table on the Bow Wow child is the normal force. Gravity on the Bow Wow child gives the object its weight. So in this particular instance, both forces that are acting on the Bow Wow child. See, we're not talking about the force on the table. We're talking about the force on the Bow Wow child in this picture. Okay. And so the normal force and the weight are equal and opposite. So those forces are balanced. That is a prime example of Newton's first law. The forces are balanced. There is no net force. Therefore, the package stays at rest. Okay. Normal force. Tension. As I mentioned, tension is what we assert, the force we, you know, attribute to cables or tensions or rope. And so if you attach a rope or a cable to an object and you pull on that rope or cable, you're exerting tension. Now, the thing about the tension is that we assume that all of the tension exerted on the rope is transmitted to the object that is attached to. So if I exert a force on the rope, all of that force gets applied to the object that the rope is attached to. So tension, okay? And you can see in the picture that we have an object with a mass M, and you have gravity pulling down on the object, giving the object its weight, and we have tension being exerted on the object as well, pointing up. So you can see in the free body diagram, see they took that big old block M and collapsed it down into a dot. And the tension is pulling up, the weight is pulling down. Those two forces in this particular picture are balanced. And so the object is not going to accelerate. The object is not going to accelerate. We didn't say the object is not going to move. We said the object is not going to accelerate. Why? Because all the external forces on the object are balanced. See, the tension in this particular case is on an object that is in motion. When we look back at the object sitting on the table, these are balanced forces on an object that is at rest. Okay, so just be mindful of that. And then here there are, this is just an overview of the 4 fundamental forces in nature. Okay, so you can see that the gravitational, electromagnetic, weak nuclear, strong nuclear forces, those are the fundamental forces in nature. And you can see how strong each of those forces are. Now, you would think that, since gravity deals with the masses of objects and those objects can be very large or very small, you would think that gravity must be the strongest force. But actually, gravity is the weakest force. It's the weakest force. Okay. If you look at the strong nuclear force is the strongest force. Okay. And you can see also, the relative range or relative strength of those forces, and then the fundamental particle that is associated with each of those forces. Okay, so not that you need to know anything about that. That's just, we're definitely not going to use anything that deals with the electromagnetic or nuclear forces, just to know in nature what forces are there. and to have in your mind, um, how much weaker gravity is compared to the others. All right. All right. So that is pretty much what I wanted to share with you regarding Newton's laws of motion. Um, I'm going to stop share now and open up the floor. I know, we're finished a little bit. Normally I'm running right up to the time for class to be over, and even sometimes going a few minutes over. But, I guess it's a good thing today. I do have a few minutes. And if you have any questions about what I've covered here today or anything, regarding this class, don't hesitate to ask. Just unmute, ask your question. I will take that silence to mean that everybody is good. Oh, I'm sorry. I see a question just popped up. Uh, well, in terms of its actual strength compared to the other forces, it's the weakest force. You can think of it this way. It takes a whole lot more force to keep the nucleus of an atom together compared to the amount of force, gravitational force, that objects exert on each other. Okay. And I don't, why it works that way. Well, that's, the only explanation I can give is because that's what scientists have uncovered through investigation and experimentation. But why it turned out that way, I don't have a firm answer to, other than that's probably a question beyond science, why it works that way. Um, you can think of it this way: the fundamental particle that gives objects mass um, is a does not those particles do not exert as much force on each other as the particles that we're dealing with on a subatomic level, like electrons, protons, muons, gluons, leptons, muons, all the things that are associated with the nucleus of an atom. Okay. And you could also think of it this way too: gravity is a force that depends to a large degree, is kind of this action at a distance force. Whereas some of those other forces, um, the distances aren't necessarily as big in most cases, because we're dealing with subatomic particles, which are in closer proximity to each other. I hope that makes a little bit of sense. Miles, did that take care of your question? I noticed you're typing in the chat, so yeah, thank you very much. Anybody else who has questions, don't hesitate to unmute or type your question in the chat. So, since there are no more questions, we are done for today. I'll hang around just a few minutes more, and then I'll stop the recording and make it available in the announcements. It usually takes about 24 hours or so for YouTube. They've been running a little bit slow lately, so I do apologize that I didn't get the recording out there sooner. there are no questions, you're free to go. We're done.
Thank you. Have a good day.
You do the same. Take care. Thank y'all so much. Y'all make this so easy for me. Thank you very
Thank
much.
you.
All right.